Welcome back, everyone. Today we're going to talk about electric potential energy. We've talked about potential energy in 140 and energy in general. We'll do a little bit of review and then talk about the big picture. So a reminder, work is how we started defining energy. Work is, one way to define it is force dotted into displacement, delta R or sometimes D. So for example, this box here is if it moves from here to here and exerts a force on it at an angle theta and the displacement is in that direction, the amount of work done is force dotted into the displacement, or F times the displacement times the cosine of the angle between them. So work is the energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. So when the angle is less than 90 degrees, it's positive work because cosine of theta is positive. When the angle is greater than 90 degrees, the force is taking energy out and the cosine of the angle is negative, so we get negative work. So let's have a look at an example here. We have a box that moves 3 meters to the left. And when it's moving 3 meters to the left, there are 3 different forces on it, and it's asking what is the net force on the trunk. I guess it's the trunk. What is the net force on the object? Well, here's the 3 forces, right? 5 newtons, 9 newtons, and 3 newtons. So let's do the first one. So work is equal to, on 1, so the work due to the first force is going to be the first force times the displacement times the cosine of the angle between them. And you'll notice here that the force and the displacement are in the same direction, so the angle between them is 0. So that cosine of 0 is just 1, and so F1 times D ends up being 15.0 joules, right? 5 newtons times 3 meters. The work for the second force is going to be the work of the second force times the displacement, which is still 3 meters, times the angle between them. And if you look here, this here in the top right corner, this is the actual angle between the displacement and F2. And since that's 30 degrees, this is 150 degrees, so it's the cosine of 150 degrees. And when you plug that into there, you get minus 23.4 roughly joules. And work for 3 is equal to F3 times D times here is the angle between them is 90 degrees. This is just to remind you, right, that when the angle between them is 90, there is no work done because the cosine of 90 is 0. So the work here is 0. So if you combine all these together, the total work is the sum of all the works, right? Work 1 plus work 2 plus work 3. And if you add all 3 of those together, you get, it looks like a minus 8.4 joules, roughly. Reminder about some of the other sort of parts of energy and energy conservation. The kinetic energy is the energy of the motion of the object, and that's 1/2 mv squared. So it depends on how fast it's moving. It depends on the speed and the mass. The potential energy is the energy in the system that is stored in the system. So an example we did in 140 would have been, or in the previous physics course would have been gravitational potential energy or spring potential energy. And we're going to do one for electrical as well. And change of potential energy is defined as -1 times the work done by the forces. So change of potential energy is equal to minus the work. And this is always true for conservative forces. Forces where the amount of energy change between 2 points is independent of the path. It's unlike things like friction and things like that. But our electric force is conservative force, so we don't need to worry about that. So every conservative force with a potential energy, as we saw before for gravitational potential energy, there is more potential energy the higher up you are from the ground. So for example, if I have an object here, right, and the force of gravity is downwards, the height is mgh. And if it's higher up, the potential energy is going to be higher. So if I go from here to here, there's going to be a change in potential energy. Example here. Which of these 2 rocks has more gravitational potential energy, A or B? Give you a second to think about that. Pause it if you need to. it's rock B. It's higher up, right? The higher up it is, the more potential energy it has. As you move it up, away, when if you go here, if you move it away, the gravity is doing negative work. It's sort of, you're storing energy in the gravity rock system. The same is true for electric potential energy. So if I have a uniform electric field, like a constant electric field like this, just an electric field pointing right to left. Remember in the previous examples we had the gravitational field pointing downwards. But if I have a constant electric field pointing right to left, then it's going to be the same thing. The force is going to be Q times the electric field. F here will be Q times E. And if I move from right to left, the force is doing work as the particle moves along this delta R here. And you can show that the potential energy in a uniform electric field. So this is potential energy for a uniform E field. It's energy stored in the charge at different points. So if the charge is way over here, it's going to be at a very low potential energy. If it's up here, it's at a very high potential energy. Think of a positive charge, right? If I move it this way, I'm moving it against the electric field, so I'm spending energy to move it out here. I'm storing it in the potential energy. And when I let it go, it's going to naturally fall to a lower potential energy. Which of these two positive charges has more electric potential energy? I'll give you a second to think about it. And higher potential energy would be here, because think about it, if you're moving it this way, you're going against the force. The force, this is the direction of the electric field, right? And it's the direction that the force will be that way. So if I'm moving the charge this way, I'm going against it, and I'm spending energy to store it here. And if I let it go, the positive charge here is going to fly towards the negative side. So that's a higher potential energy. So once again, if I have a positive charge in a uniform electric field, right, the further against the electric field, the higher the potential energy. And if I let it go, it moves towards a lower potential energy, towards the negative. The positive will be attracted towards the negative. And it'll be the opposite for a negative charge. This is something that's not the case in gravity, right? For the negative charge, since the potential energy is, don't worry about this U naught, you can just add any number you want, but since potential energy is QE times the position, since Q is negative, this is going to be a higher potential energy. This will be like very, very, very high potential energy, and the potential energy is going to decrease as you go in this direction. All right, so this would be like, you have to spend energy to move the charge this way, and if you let the negative charge go, it's going to go towards that direction. The charge will move towards a lower potential energy on its own. Here's an energy diagram showing a positively charged particle in a uniform electric field. So let's say the total energy of the particle is this here, and I place the particle at S max, at some location S, and I let it go. And then this here, so that's the total, the brown line is the total energy, this is the potential energy. And so if I let go of a charge, it's going to move towards a lower potential energy. And the loss of potential energy turns into kinetic energy. So at this point here, the potential energy went from maximum to here, and that difference changed into kinetic energy. So if you were to look at it a little bit further down here, down at this point here, it would be moving faster, and there would be less potential energy. Two negative charges are equal. Which one has more potential energy? Give you a second. And that's because it's a negative charge, so the higher potential energy is going to be towards the negative side. Positive charge moves as shown. What's going to happen to its kinetic energy over time? You can do this energy-wise or force-wise. What is it going to increase, remain the same, or decrease? And it's going to decrease because as it's moving to the right, the force is going to be to the left, slowing it down. It's going to a higher potential energy, which means it's going to a lower kinetic energy. So if I were to do that graph again, right, here's the total energy, and here's the potential energy here. Right, so as the particle is moving this way, right, it's going this way, its kinetic energy decreases, and so it'll be moving slower. So work, when it's a constant force in a straight line, it's just F dot displacement. But in cases where it's a slightly more generalized, it's a force along a motion along the x-axis, and the force changes, the force is not constant, then it's an integral of the force over that displacement. So in this example here, I have a particle going from x initial to x final, and the force on the particle changes as it moves across. And for an F times x diagram, then the work done is going to be the area underneath this, which is just going to be the area of that. So here's an example that I would like to do. So I'm just going to scratch this one out. So block is initially at rest, and at Fx initially at rest, and its force as a function of position is 2.5 times minus x. And it's asking, what's the kinetic energy when it reaches 2 meters? So let's write down everything we know first and figure out how we're going to do that. So it starts at rest, and we want to find its final speed, right? Its x initial, we'll call it 0, and x final is 2 meters later. And its mass, which may not come into play here, is 1.5 kilograms. So things that we can use, equations that we can use here to help us solve this, the main one is going to be work is equal to the change in kinetic energy. Or I'll flip that around when I use it. And remember that kinetic energy, well, actually we don't really need this one, but it's a half mv squared. And also the other equation we're going to need is how to calculate the work for that given force. So let's do our solution. All right. So I'm going to say that the change in kinetic energy is equal to the work done. In other words, K final minus K initial is equal to the work done, which is the integral of the force as a function of x dx from x initial to x final. Since it starts at rest, K initial is 0, and so we just end up with K final. And I'm going to plug in for the force, right? So it's the integral from x initial to x final of 2.5 minus x squared dx. And when I integrate that, what do I get? Well, I end up with 2.5x minus, what does that look like? X cubed over 3, right? Between x equals x initial, right? X initial is 0 and x final is 2 meters. X initial and x final. So when I plug in the endpoints, I end up with 5 minus 8/3 joules, which works out to about 2.33 joules. So that's the energy. That's the change in kinetic energy. It gained 2.33 joules in kinetic energy as it moved from x equals 0 to x equals 2. Let's apply this for something else. Also, this is even more general. Before I get to that, this is even more general when the work is the integral of a force dot a displacement. So if I want to integrate a particle moving along some weird path with some varying force, it's a line integral over that whole thing. We won't need to do line integrals in detail, but that's how you do it. I would like to do this for two charges, Q1 and Q2, separated by a distance. Initially, we'll keep 1 at Q1, and 2 is going to be at x initial, and we're going to move Q2 from x initial to x final. And remember what the force between Q1 and Q2 is. It's the electric force. It's going to be K Q1 Q2 over R squared. So we're going to use that to calculate the work done as it moves from there, because as it gets further away, the force gets weaker. So I can calculate the the work done in this case. So it's the integral from x initial to x final of K Q1 Q2 over R squared dx. I'm going to pull out the K, Q1, and Q2, right, because they don't matter. And it's the integral, integral x squared. So let me quickly fix that. We're using x instead of r in this case, so the integral of x squared. So what's the integral of x squared with respect to x? Give you a second to remember how to do that. K, Q1, Q2, it works out to minus 1 over x is the integral of 1 over x squared between x initial and x final. And so I'm going to rewrite this as, I'm going to factor out a minus sign, and you'll see why in a second. K Q1 Q2 over X final minus K Q1 Q2 over X initial. Okay, so using that, we can say, well, our definition for change in potential energy is equal to minus the work. So it's equal to K Q1 Q2 over X final minus K Q1 Q2 over X initial. So that we're going to use that to define the potential energy stored between two charges as K Q1 Q2 over R. That is potential energy stored between two charges. And we can use that to solve all kinds of interesting sort of conservation of energy problems. All right, so our electric potential energy between 2-point charges is K Q1 Q2 over R, or remember K is just 1 over 4 pi epsilon naught is the other way to write that. So let's do a simple example. Let's just calculate the energy stored between these two charges. And this should be nanocoulombs on either side. So there's two charges. One is plus 1 nanocoulomb and the other one is minus 4 nanocoulombs. And this should not be squared, obviously. So the potential energy, K Q1 Q2 of R, let's calculate it. Well, let's write down everything we know first. So we'll call Q1 1.00. And remember, nanocoulomb is 10 to the minus 9 coulombs. Q2 is minus 4.00. That's the other charge times 10 to the minus 9 coulombs. The distance between them is 2 micrometers. And if you remember, a micrometer is 10 to the minus 6 meters. And for K, for today, I'll use K as approximately 9.00 times 10 to the 9 newtons meter squared per coulomb squared, which is also 1 over 4 pi epsilon naught. So I can use all this to calculate the potential energy, right? Just plug in everything into here, Q1, and I get an answer. Since one charge is positive and one charge is negative, we have an answer of minus 0.0180 joules, assuming I did those calculations correctly. We have negative energy. That's okay. Potential energy can be negative. You can set the 0 to be whatever you want. All that really matters for changes to kinetic energy are changes in potential energy. So that's potential energy stored between those two charges. So let's look at a couple different examples of how we can use potential energy, right, K Q1 Q2 over R, to look at the behavior of particles. Consider two positive charges, and they're both initially moving towards each other. So there's a plus, they're moving towards each other. Since as they're moving towards each other, what's going to happen? There's going to be a repulsive force, and they're going to slow down, and they're going to reach some minimum separation and then start to moving away from each other. That's sort of represented with these little arrows. If you look at it energetically, it kind of looks like this. If I plot the total energy of the particle, E mechanical, as a function of the distance between them, at this distance, right, this part here is the kinetic energy stored between them, and then the remaining part is the potential energy. And as they get closer and closer together, the kinetic energy gets smaller and smaller until at this point right here, they have stopped moving. And since there's still a force between them, then they'll start moving apart and speeding up again. So this r min will be the distance of closest approach. Another example of that is if I started with a positive and a negative charge, equal and opposite charge, and I fired them away from each other, well, they would start moving away depending on how hard I fire them, and they would slow, because there's an attractive force, they would slow down, and maybe they would stop, and then they would start moving back towards each other. And this is another way of looking at it. Let's say the total energy of the charge of the particle is this, right? This part here, the difference between these two is the kinetic energy. So if it starts here, the difference between them is the kinetic energy, and as they get closer and closer together, their kinetic energy goes to 0, and this is where they stop. And this will be the distance of maximum separation, or R max. Then they would move back closer together. So, positive and a negative charge are released from rest in vacuum. They move towards each other. As they do, Is it a positive potential energy becomes more positive, positive potential energy becomes less positive, negative potential energy becomes more negative, negative potential energy becomes less negative, or positive potential energy becomes a negative potential energy? While you think about it, let me write down the equation. And let's do the answer. A negative potential energy becomes more negative. Let's think about that. It's negative because one charge is positive, one charge is negative. So the product is going to be negative. So it's always going to be a negative energy. And the potential energy is going to get larger as they get closer and closer together, because R gets smaller, which means this becomes a larger number. So let's do an example. A proton is fired from far away at a 1 millimeter diameter glass sphere. So here's my proton. It is far away, and it's fired at a 1 millimeter diameter glass sphere. So here's the glass that's been charged to 100 nanometers. Okay, what initial speed must it have such that it just reaches the surface of the glass? So when it reaches the surface like this, it's just enough to reach the surface and stop. Here, actually, I have a better drawing of it here, right? So it starts, I fire it from really, really far away with V initial, and basically, by the time it gets to the surface, it just comes to a stop. Now, really, really far away in these examples usually means that R is essentially infinity. And since U depends on 1 over R, we can treat U as 0. So really far away means that it's initially so far away that there's virtually no potential energy stored between them. So we can do conservation of energy for this, right? The energy at the beginning is equal to the energy at the end. So here's how it's done. Conservation of energy. K final plus U final equals K initial plus U initial. So K initial is just 1/2 mv squared because it has some initial speed. We want to find what that initial speed is. U initial, we're setting to 0 because we're saying it's crazy far away. And we want to fire it such that K final is 0. It stops right when it's at the radius of the sphere. So the potential energy will be K, charge of the proton, charge of the sphere over R. So here's our equation. Conservation of energy, solve for V initial. And the charge on the proton is E. The charge on the sphere is given as 100 nanocoulombs. So solve for V initial, and you plug in everything, and we see that if you want to do that, you have to fire that proton with initial speed of 1.86 times 10 to the 7 meters per second. That's a fraction of the speed of light. That's pretty fast. Here's another one. Imagine two particles, an electron and a positron. A positron is just an anti-electron. It's just an electron that has a positive charge. That's a real thing. Look it up. If I have an electron and a positron, so they have the same mass but opposite charge, and they start off 100 femtometers away from each other. Femto is 10 to the minus 15 meters. And they start there, and I fire them away from each other with the same speed. Basically, I want to know, if I don't fire them strong enough, they'll start moving apart and then they will move back together. But I want to be able to fire them with enough initial velocity such that they can get infinitely far away from each other. If I fire them too softly, they'll come back. If I fire them strong enough, they can get away from each other, i.e., it's called escape velocity. So I want them at the end for them to be essentially infinitely far apart to have V final of 0. So how hard do I have to fire them such that when they get infinitely far apart, their kinetic energy is just barely 0? So it's a conservation of energy thing, right? K final plus U final equals K initial plus U initial. So K initial, they each have kinetic energy 1/2 mv squared, so I put it in twice. The potential energy initial, they both start at some initial really close distance, right? 100 femtometers. That's the final energy. The initial energy, they're infinitely far apart, so the potential energy is 0, and I want them to just come to a rest at infinity, so they have 0 kinetic energy at the end. So I basically have 0 equals this. Once again, solve for V initial, and if I want that electron, that anti-electron to escape each other, I need to fire them with an initial speed of 5 times 10 to the 7 meters per second. You can do this with lots and lots of charges. If I have 3 or 4 charges, I can find all the potential energy stored between all of them. And I want to do just a couple examples, 2 examples of that real quick. So let's say I have 3 protons, looks like it's 3 protons, on the corners of an equilateral triangle. I want to know what's the first thing I'm asking is, and the equilateral triangle is given here, it's 20 nanometers per side. It's asking what's the total potential energy for that. Well, let's start by writing down what we know before we do all the potential energy stuff. So they all have charge plus E. Just as a reminder, E is 1.6 times 10 to the negative 19 coulombs. They are each separated by a distance, we'll call it A, is 20 nanometers, and a nanometer is 10 to the minus 9 meters. We might need the mass of a proton. That's 1.67 times 10 to the minus 27 kilograms. There it is. So now we can calculate the potential energy. So for the potential energy, you have to calculate all the possible pairs. So this pair here, between these two, what's the potential energy there? Well, it's going to be K, and then E for one of them, then Q1, Q2, then the distance between them is A, right? That's for that pair. But it's going to be the same as the energy between this pair and the same as the energy between that pair. So each pair, it's the same distance, it's the same charge, so it's just going to be 3 times that. Okay, so it's actually just going to be 3 times K times E squared over A, which 3.456 times 10 to the minus 20 joules. That's how much energy is stored between those three. So all that could be converted into kinetic energy. The second question asks, what if I were to release them? What would happen? Well, if I have three protons and I'm holding them there and I let them go, they're all gonna exert repulsive force on each other. So if I release them, they will start moving away from each other, and after a certain amount of time, they'll be really, really far away, and they'll be moving away from each other like this, right, with V final, and we'll assume that R is going to infinity. So how fast are they moving when they're really, really far apart from each other? Well, that's a conservation of energy problem. So let's see. E initial equals E final. So it's K initial plus U initial equals K final plus U final. So K initial is 0 because they're all at rest initially. And then potential energy, well, we saw that already. We'll just put it as 3 K E squared over A. And then K final, well, there's 3 of them, and they each have kinetic energy 1/2 mv final squared. That's the kinetic energy for each of them. And U final, if they're really, really, really far apart from each other, that's 0. So I can solve that for V final, kind of like what we did with the other ones. Square root of 2K E squared over the mass of the proton times A. And when I worked it out, I got approximately 3,700 meters per second, give or take a meter per second. Okay? So that's one way you can use that to calculate change in kinetic energy of particles using conservation of energy. One more problem I'd like to do. Let's just calculate the total potential energy stored in this arrangement. It's 4 charges. Each charge has a value of minus 4.00 times 10. It's microcoulombs, 10 to the minus 6 coulombs. And they are all a distance. They're on a square, so they all have the same distance, 4.00 times 10 to the minus 3 meters. So what's the total potential energy stored in this? Well, to do that, we need to calculate the energy stored in each possible pair. So there are multiple pairs here. Because there's 4 of them, we have to look at every possible combination, right? So there's going to be a pair here, separated distance A. There's going to be an identical pair here. There's going to be an identical pair here. There's going to be this pair here. So let's do those 4 first. So the total potential energy is going to be 4 times that's stored in each pair, K Q squared over A. But some of you may have seen what the other 2 pairs are. There's also potential energy stored between these 2. And using Pythagoras, you can show that that's root 2 over A, and that's also root 2 over A. So there's 2 more pairs, the kitty corner ones. So plus 2 times K Q squared over root 2A. And when I did the calculation, I got, you can simplify this. I can factor out a 2k q squared over a here, and I end up with 2 plus 1 over root 2. And that works out to approximately 195 joules. Okay, so that's the basics of calculating potential energies and using conservation of energy problems with electric fields.